Hello guys, I hope you're doing fine. Welcome back to another video. So in this video I will be teaching you guys how to design the layout of a CMOS NAND gate. So you can launch Layout Excel. I have already launched it here. So let us look at the schematic of a CMOS NAND gate. So it consists of two PMOSs between VDD and output and in parallel, and two NMOSs in series between VSS and output. So in the layout we can go ahead and instantiate two PMOSs and two NMOSs. So in the layout window, press I, go to browse, open the 180 nanometer library, select for PMOS, view layout. So we need two PMOSs, and you can instantiate two NMOSs as well. Now these are the blocks of the PMOS and NMOS. Now to view the internal structures of the transistors, you can press Shift plus F. So these are the internals of the transistors. Now let us look at the sizing of the transistors. The length is 180 for all the transistors, whereas the width of the PMOS is 800 nanometers each. So you can select both, press Q for properties, and make them. Total width is 800, so let it be as it is. And in PMOS the width is 400, so let it be as it is. The widths and lengths are correct. So coming to the schematic, the source of one of the PMOSs is VDD and the drain is connected to output. So coming to the layout, the source, that is this terminal, is VDD, the other, that is the drain, is output. Now coming to this PMOS, again the source is VDD and the drain is Vout. So here the source is VDD and the drain is Vout. So we have two PMOSs between VDD and Vout. So what we can do is we can share VDD and Vout. So what we can do is we can share the two drains. So we can share this and this. So to share them, we can move it, or we can overlap the transistors one over the other. So go ahead and press M for move and move them, overlap the two contacts. So now what we have done is we have shared this connection. So it is VDD output, output VDD. So it is the same thing, VDD output of the first transistor, output VDD of the second transistor. So now coming to NMOS. The two NMOSs are in series between Vout and VSS. So if we consider one of the terminals as VSS, that is, let us consider this as VSS, the other, that is, this is VSS, the drain becomes another short with the other source of the other PMOS. So this and this are shorted, so we can again overlap them. So it is configured as VDD, VSS, and this is this short, and this is Vout. So it is a good layout. So it is a good layout practice to place all PMOSs in one row and all NMOSs in the other row. So now let us look back at the connections. So this is VDD, Vout, VDD, VSS, short, Vout. So we have to short this Vout and this Vout, and combined is the Vout of the NAND gate. So the leftmost and the rightmost terminals are VDD, this is VSS, and this can be left as it is. So let us go ahead and short the two outputs. We can use a metal. So once shorted, we will have to, now coming to the gate connections, one NMOS and one PMOS, the two gates have the same common input. So coming to the layout, one PMOS and one NMOS, the gates have the same common input. So we have to short the gates, that is, we have to short this gate and also this gate. So now let us do the VDD and VSS connections. For that, you can press O and you can instantiate a N-well tab. This forms the tab for VDD. You can increase the rows, increase the columns, and place it above the PMOS. And for the VSS connections, you can instantiate P sub tab, that is M1 to P sub. Increase the, you can place it below the NMOS. So this becomes the VDD and this is the VSS. Now as I mentioned earlier, this is VDD and this is also VDD. So you can short them directly using metal 1. Now coming to the NMOS, only one VSS connection. You can short it using metal 1. You can take it a bit lower. Now coming to the gate connections, let me go ahead and maximize the window. So for the gate connections, as I mentioned in my previous video, we need a metal 1 to poly short or via. So you can add it here. This forms the input A and this gate is the input B. As since we don't have space in the between, I will place it over here. And you can draw a path of poly shorting them. So now this is A, and this is B, and this is V out, VSS, VDD, I think the circuit connections are fine. So we can place pins. So we press Ctrl P, place A and B, VDD, VSS, and Vout. You can create labels as well by clicking this checkbox, and you can also go to options and choose the height. Let us make it 0.03. Now we need to place a metal 1 pin. We don't need to place a poly pin. So for that you can unselect use, type in metal 1 pin. Hit Ctrl P again. And now you can place pins. So we had named it A first. This is A. B. VDD. VSS. And Vout. So now we can go ahead and run DRC. First check and save it, and you can run DRC. Choose the technology file, hit OK. So we are faced with a few DRCs. So it says P implant to P implant spacing must be greater than 0.4 micrometers. So select it and press this arrow here. So it says the minimum space between two P implants must be greater than 0.4 microns. So what we have here is only 0.36. So what we can do, the simplest way is, since it is P implant and both the transistors, the source and drain are shared, so we can draw a rectangular P implant here, filling the gap. So that takes care of the error. Also you could do the same for NMOS, but yeah, there is a sufficient distance between them. So what about the next error? Poly width must be greater than 0.18 micron. Okay. So you can draw a path of poly here. So what it says that the poly to poly short must be greater than 0.18. So previously what had happened was it was shorted from here to here, which is 0.16, which is lesser than 0.18. So let us make it 0.18. So now you can see there is 0.18 and it is satisfied. Now poly to poly spacing must be greater than 0.3 microns. So it's the same error. Now it is resolved. So contact shapes must be rectangular. Yeah. So as I mentioned earlier, we have to carefully overlap the two transistors, and the contact must form a perfect square. So as you can see, it is not a square, it is off by 0.01 microns. So we'll have to place it perfectly on top of each other. Use the bind key K for ruler. So it is not yet perfect square. So you can place another NMOS. Yeah. So now it is a perfect square of 0.2 into 0.2 micrometer. So check and save. Just close the previous run and run the DRC again. So we are faced with a few more errors. Okay, so I had not completely dragged it. I had now, so make sure to short the connections properly. So metal 1 to metal 1 spacing. So metal 1 to metal 1 spacing. Let us close that run and run a new DRC. So there are no DRC errors found. So the next step is to run LVS. Choose the schematic, layout, technology file. Okay. Yes. So here what the error is that I have shorted A and B. So I have shorted two different polys and given the pin as A, and shorted these two polys and given the pin name as B. So there is an error. What I have to do now is interchange A and B. So it is saying that the schematic is not checked and saved. So make sure to check and save the schematic. So we are faced with a few LVS mismatch errors. So let us look at what they are. There's parameters, open tool. You can probe it or zoom it. Yeah. So it is clear now. The width of this NMOS is 800, but the width of this NMOS is 400. So what is the error? This should be also 400 nanometers. Check and save. Close the previous run. Save. Run LVS. So we have successfully cleaned the DRC and LVS errors. So this video has given you guys a good example of what types of errors you can be faced with during LVS and DRCs. So they are pretty simple. and the tool tells you what are the errors and you can correct them quite easily. And you have to get LVS and DRC clean in order for it to be a good layout. So this is it guys, the NAND-Gate layout design. So it is not very optimized, we can optimize it further, but for now this is enough. And in my next videos I will be discussing the common source and op-amp layouts. So stay tuned. Thank you for watching.